video, I will be trying to solve another KTU problem. So this problem is from MoS S3 Civil. So this was asked in 2017-10. This is the old scheme, not the 2019 scheme. But this can be asked in the new scheme also. Now, what I feel is this question was asked for 10 marks, but then it's a lot of time-consuming question because of the nature of the problem. The question is, a cast iron beam has an I section which top flange 80 by 40, web 120 by 20, and bottom flange 160 by 40. If tensile stress is not to exceed 30 MPa and compressive stress 90 MPa, what is the maximum UDL the beam can carry over a simply supported span of 6 meters if the larger flange is in tension? Okay. Now you have to observe one thing. The dimensions of the I section. It is an I section. It's a beam. Uses an I section uses a beam. So if you are not familiar with these terms, I'll just explain it what it is so that you can learn now. So this is what is known as flange. This also what is known as flange. Okay, and this the center portion, that is what is known as web. Okay, this is known as top flange, this is web, and this is bottom flange. So I hope this is clear to you. I'm just giving you an idea. Now they are telling the top flange is 80 by 40. So this dimension is 80 by 40. Web is 120 by 20. So this is thickness is 120 and the height is 120. 120. And the bottom flange is 160 by 40. 160 by 40. Now this is not symmetrical. This is symmetrical about y-axis, not symmetrical about x-axis. Okay. Now that is the complication of this problem, which I feel it is making it a little time consuming. Now what is the other data given in the problem? It is given that the tensile stress, maximum tensile stress is given as 30 MPa. And maximum compressive stress is given as 90 MPa. Remember that 1 MPa is 1 Newton per mm square. Okay. Now this has to be used as a beam of length 6 meters, simply supported. Okay. Now there is a UDL on the beam of the magnitude W, which they are asking us to find. W. Okay. Now this is 6 meters. Now the maximum bending moment of simply supported beam, which you are expected to know, is WL square by 2. The bending moment diagram of a simply supported beam looks like this. It's a parabola. Sorry, it's a parabola. Okay, and this maximum is at the center. This value is nothing but WL square by 8. So this you are expected to know. Simply supported beam, the maximum bending moment is WL square by 2. Now why we need maximum bending moment? So those things we will explain. One more thing it is given here. The larger flange is in tension. Now what is the use of this? It is because if you take a cross section here, so let's say AA. Okay, so AA can be this. It can also be this. So this beam, how you place it? You can place this top flange, a longer flange at the top. You can also place it like longer flange at the bottom. Now the larger flange is at tension. So they're telling the bottom flange, this largest flange, it is in tension. So it will be only in tension when in a simply supported beam, the beam will bend like this. So top of the beam there will be compression, the bottom of the beam there will be tension. So bottom of the beam is tension, and they're telling larger flange is in tension. So that means the larger flange is in the bottom. So that means this is the orientation that you have to take, not this. So that is why this data is given. Now that is done. Now once we have done this, we have got all the details. Now remember, bending stress is due to bending moment, and bending stress is maximum where bending moment is maximum. So that is why we have to find the maximum bending moment in the beam. So there is a bending moment here which is less than this value. So there will be bending stress at this section, but in this section the bending stresses will be lesser than this section. So for this beam, the maximum bending stress will be at this point at the center, because the maximum bending moment will be at the center. Okay. Now the bending equation is what we have to use. Bending equation. The bending equation is given by m by I equal to sigma yy equal to E upon R. Now m is moment, bending moment, I is the moment of inertia, sigma is the stress, y is the location from the neutral axis. At what point we want the stress. E is Young's modulus, R is radius of curvature. Okay. Now this there is a mnemonic to remember this. It is may I see you Elizabeth Rani. C for sigma, SCE. Okay. So there you can remember like that. Now this first portion only we will use. Now one thing that you want to know is bending moment. We know in terms of W. I we have to calculate. Sigma is given. Y also we can calculate from the section. So now the task is to find the I. Okay, we want to find the I. So I about the centroid. Now let's say this is the centroid of the beam. I don't know where it is the centroid. Somewhere here, let's say. So this is an axis that I have drawn from the centroid, which is passing through the centroid of the beam. Now in the vertical line, it will be at the center because it is symmetrical in this vertical axis. This we don't know where is the location of this horizontal line. Okay, so the only thing is this is the centroid. It is passing through the centroid. This is the centroid. Now first thing is we have to find the centroid. Then we have to find moment of inertia of this beam about the centroid in this axis. So this I is about this we have to find this axis. Now that is a task here. It involves a lot of task, calculations, simple calculations, but there can be many chance of making mistakes. Now how do you find the centroid? The first task is to find the centroid location of the beam. Now for finding the centroid, what we can do, we can divide this into 3 areas. Okay, so what I'll do, I'll make a copy of this for centroid calculation. Let us create a temporary axis here. Let's say at the bottom. So we will try to find everything with respect to this bottom. Okay, so now let's say this is the centroid location. This centroid location I'll call as y bar. Okay. Now how do you find this? It's simple. We have to divide this into 3 areas. So let's say this is area 1. So let's say this is area 2. And let's say this is, we have one more area. Area 3. Okay, so total area is A1 plus A2 plus A3 is nothing but 80 times 40 plus 120 times 20 plus 40 times 160. So this, we'll quickly calculate this. So this is 80 times 40 plus 120 times 20 plus 40 times 160. So this is 12,000. 12,000 mm square. This is the total area. Okay. Now we have to find the centroid. So we know that centroid can be calculated using the formula, this formula, that is A y bar will be equal to A1 y1 bar plus A2 y2 bar plus A3 y3 bar. Okay. Now what is that? It is nothing but this area, its centroid from this line, plus this area into its centroid from this line, this area into its centroid from this line. So we are just seeing the vertical distances, not horizontal distances. Horizontal distance we don't know, we don't want to find. Okay. So what is A1? A1 is nothing but, we have written here, it is 80 times 40. Now what is y1 bar? Y1 bar is the centroid of this area. Centroid of this area. That is this location. So this is basically 40. So this centroid location, this will be 20. This will be 20. So centroid will be 40 plus 120 is 160 plus 20 is 180. Okay. Plus what is A2? A2 is 120 into 20. Centroid of A2 is here. It is from this point. It is, this distance will be 60. Total is 120. So this, from this point, this will be 60. So 40 plus 60 is 100. Now what is A3? A3 is 160 into 40. Distance of centroid is, this is a centroid, this will be 40 by 2, that is 20. So all distances we are measuring from this. Okay. So this, so we can say y bar equal to divided by area. So area is nothing but 12,000. So this, let's calculate this very fast. What will be the value? So this is 80 times 40 times 180 is 120 times 20 times 100 plus 160 times 40 times 20 divided by 12,000. So this comes out to be 78.66. Okay. 78.666 mm. So this is a centroid. From this distance, it is 78.66 mm from the. So that we have got. What is the distance we have got? Now, what we have to do is we have to find the moment of inertia. We have to calculate the moment of inertia. Moment of inertia about centroid. So for this we will use the parallel axis theorem. So parallel axis theorem tells us that if you have a body, some shape, it has a centroid. If you know the moment of inertia of the body about the centroid, IC, we can find the moment of inertia about this any axis by this equal to IC plus area into h squared. H is the distance between center of this axis in which we know the moment of inertia to the axis in which we want to find the moment of inertia. Okay, so moment of inertia about the centroid axis plus area into h square will give me moment of inertia of this area about this axis. Okay, this is what we are going to use. So what we have to find is we have to find three moment of inertia. First, we have to find the moment of inertia of this body about the centroid. Then we have to find moment of inertia of this body about the centroid. Then we have to find moment of inertia about this body about the centroid. Okay, that is what we are going to do now. So let's say I'll just make a copy again so that it is more clear to you. So don't make a lot of copies in your calculations when you're doing for exam. So I'll keep a copy here so that I can take it later on. So let's say we'll first find. So I'll draw my axis here. This is the original axis. Sorry. Okay, and we know this distance. We just calculated this distance. This distance is nothing but 70. What is the value? 78.66. So 78.67. Okay, so this is the distance. Now we will find moment of inertia of this body, or let's say moment of inertia of this body about the centroid. So what I'll do, I'll remove the other bodies. So this is not required. So this is not required. So this is not required. All the dimensions I can remove. Okay, this 160 by 40. We know that how to find moment of inertia of this body about its centroid. This axis. Okay, I hope that is everyone knows this of a rectangle. So this is nothing but B 160 into D cube 40 cube by 12. Okay, and what is this distance? This distance also we can measure. What is it? Measure in the sense we know what this distance. This distance is nothing but total distance is 78.67. 78.67 minus 20. So it is 58.67. Okay, 78.67 minus 20. This is 20 because it is passing through the center. So 78.67. So moment of inertia about this point, this will call as I1, is nothing but 160 times 40 cube by 12. So that is value of I plus AH square. Area is nothing but 160 times 40. H square is nothing but 58.67 square. So this comes out to be, let's calculate this very fast. 22883214 mm raised to 4. So this is the moment of inertia. This is I1. This is the moment of inertia of this rectangle about this centroid. Now we will find for the second portion. So that's why I made this here. I kept it here. So let's say copy here. Let's just bring it here. Now what we will see, we will find the moment of inertia of the second portion, that is the web. So let's say, so I'll remove this, I'll erase this, I'll erase this. Okay. Only thing I should have drawn here is the origin line. This line I have not drawn here. So let's say, so this line is there. Okay. Now we know this distance. This distance I have already told you. This is nothing but 78.67. Okay. Now this is we know the centroid of this this rectangle also. It is somewhere here. It is nothing but you know the distance. This is nothing but, this distance is 120/2, that is 60. Okay, and this distance we know it is 40. How do we know this? We know that this is a 40, this is 40, and this is 40. From this line, this is 40. Okay, so that means we know this distance. This distance. What is that distance? It is nothing but 60 plus 40, 100. 100 minus 78.6. Right? So that is 100 minus 78.6. That is comes out to be 21.4. Okay, 21.4. 21.4. Now, moment of inertia about this line, about its centroid, we know it is BD cube by 12. B is 20. D is 120 q upon 12. So that is the moment of inertia about this point. Now, moment of inertia about this, I'll call this I2. So I2 equal to moment of inertia about the centroid, that is 20 into 120 q upon 12 plus area into h square. Area is 120 into 20 is the area. H is the distance between the this is a central line in which we know the moment of inertia. This is a line about which we want to find the moment of inertia. Okay, the distance is h, so that is 21.4. 21.4 square. So let's calculate that also very fast. 3979104. 9104 mm to the power 4. Okay, so this is the second portion. Now one more portion we have. We just have to finish that with that portion. So let's say I'll take this. So this is the axis that we know. We know this distance. This distance is nothing but 78.6. Okay. Now we know which all we know that this we don't know. So this we don't know. This dimension is not required. This is not required. Just I'll remove this. This section is not required. This is not required. These dimensions are also not required. Okay. Now this small rectangle, we know that horizontal centroid, where is it? It is passing through the center. This moment of inertia we know it is 80 into base into height cube by 12. Okay. Now what is the distance of this base? What is this distance? This distance is nothing but, so we will come from here. It is nothing but 40 plus 120 plus 20. So 40 plus 120 is 160. 160 plus 20 is 180. So that is 180. 180. Okay. So this becomes 180 minus 78.6. So that is nothing but 101.4. Okay. So moment of inertia about this, I'll call this as I3. equal to 80 into 40 cube by 12, that is the moment of inertia about its center, plus AH square. So what is area? Area is 80 into 40. What is height? 101.4 square. So what is this coming out to be? 3332838 mm to the power 4. Okay. So total moment of inertia about the centroid is I1 plus I2 plus I3. But what is the value? Okay, so this is the value. This may not be very exact value. This approximately this is all right. 6, 7, 2, 3, 4, 5, 6, 7, 8. So this is the value that is coming out to be this final moment of inertia. Okay. Now there are a lot of rounding of here because 78.666. So if you come out with an online calculator, the value may be somewhere close to this, but not exactly this. But I hope this is acceptable. And this is the value of I. Okay, so when you calculate this, there could be some minor difference, but then it should be order of this. Okay, 6 into 1, 2, 3, 4, 5, 6, 7. 6 into 10 raised to 7. That should be the value that is coming. So this is the I. So this is the problem with this problem. We have to spend a lot of time to find the moment of inertia of the section. Once you find the moment of inertia, then it's a very simple task. You just have to use the bending equation. Now we know that the bending stress here, the varies like this. So let's draw the variation of bending stress. So top will be compression, bottom will be tension. So let me top will be compression. So it's blue here. Okay. So it will be varying like this. Bottom will be tension. The bending equation, the y is basically the distance of the point which we need. So if you want to find stress at this point, you have to find the distance here. This is y. This is y. Okay. So in bending equation, m upon I is equal to sigma upon y. So substitute the value of m at a given section, the moment will be constant. Given section in the sense we are finding at the center. So at the center, the moment is value which it's a constant value. Okay. That is WL square by 8 is the moment. So that is there. I is constant for the section. Then depending upon the y, we will get different values of sigma. If you so maximum y compression will happen at this distance when y equal to. So for compression, this will be the y, and for tension, this will be the y. So y for tension is equal to. So this we have already found. It is nothing but 78.67. 78.67. And this y is nothing but total minus 78.67. So that is, we'll just calculate that very fast. So total height is 40 plus 120 plus 40. So 40 plus 40, 80. 80 plus 120 is 200. So 200 minus 78.67 is nothing but 121.33. 121.33. 121.33. So this is the maximum compressive stress. This is the maximum compressive stress. And here we have maximum tensile stress. Okay. Now let's substitute these values, maximum stress values, and find at what moment we will get these values. Okay. So let's say sigma t is given as 30 MPa. So substituting in this equation, sigma t upon, so sigma t is here, yt, sigma t upon yt should be equal to m upon I. So m equal to sigma t upon yt into I. This is nothing but, so sigma t is given as 30. Yt is just calculated 78.61, 78.67. I we have just calculated. What is the value of I? So we'll just take the value here, 6. So 60. I don't know why it is here. So this is the value of I. Okay, So this is nothing but times 60191,256. 256. So 30 times 78.67 divided. So this comes out to be, let's calculate this very fast. So 30 times 6019,1256 divided by 78.67. So this is, so whatever value we are getting, it is Newton millimeter. So it is 53557746. 53557746 Newton millimeter. Okay. Okay. So this is nothing but, if you divide by 10 raised to 6, it is 53.56 kilonewton meter. So this we divide by 10 to the power 6. You get this. Okay. So this is the value of moment. This is for maximum tension. So reaching maximum tension. So if there is this much movement in that middle of the section, we have tension is equal to 30 MPa at the bottom. Now for maximum compression, so sigma C, the compression stress is given as 90 MPa. So it is slightly higher value, 90 MPa. So in this equation we can see sigma C upon YC equal to M upon I. So M equal to sigma C upon YC into I. So this is nothing but sigma C is 90. YC we have found out here. YC is, so this is YC. I have written Y, it's YC. 121.33. 121.33 into I is nothing but the value which you have written here, 60191,256. So what is this value? So this also will quickly calculate. So this is 90 times 601,912,6 divided by 121.33. So this is 44648586. So 44648586, 8586 Newton millimeter. So if I divide by 10 raised to 6, so 1, 2, 3, 4, 5, 6, it is 44.65 kilonewton meter. So this is scenario you have to, so this is for MC, ultralight MCM compression. So this is two scenarios. If the moment is 44.65, the maximum compressive stress is reached. If the moment is 53.56, the maximum tensile stress is reached. So that means when the moment is 44.65, the beam will break because the maximum compressive capacity has reached. So it will not reach this moment. Before that only it will fail at 44.67. So this is the maximum moment the section can take. Note this, because this is lower value. Now with respect to this, we can find the UDL. So we know that it is WL square by 8 is the maximum UDL. This value should be equal to the minimum of these two. Okay, so that means WL square by 2, WL square by 8 should be equal to 44.65 kilonewton meter. So W should be equal to 8 into 44.65 divided by L square. So this is 8 into 44.65 divided by L, the length of the beam, it is given as 6 meters. 6 meters. So it is 6. So it is nothing but 6 square. 6 square. So if you calculate this, 8 times 44.65 divided by 36. So if you calculate this, 8 times 44.65 divided by 36. So this gives me 9.922. So 9.922 kilonewton per meter. So this is the moment. It's a UDL. So this is the UDL that we can apply. This is the final answer. Now, as I told you, if I calculation, if it is given to us, then I think it is 6-7 marks you can ask. If I value is given, and if you want to, you have to calculate the centroid, I value is given, and this much portion, the remaining moment calculation is there, then you can give for 10 marks. This question should have been for 15 marks, if what I feel, given the time, not because of the complexity, because of the time. Now I think recent papers, they are taking this into consideration. But I hope this is clear. This is a little long video because of the moment calculation, moment of inertia calculation, but the remaining portion, it is straightforward. So I hope this is clear to you. We will again do another video, another question in the next video. Thank you.